Have you ever thought about finding the shortest path, not just between 2 points, but between three? It sounds simple, right? But the answer is, well, it's incredibly elegant, and it connects things like real-world engineering with the fundamental laws of physics. Let's dig into this fascinating solution, which is known as the Fermat Point. Okay, so let's start with a really practical puzzle. Picture this. You're an engineer, and you've been tasked with connecting 3 cities with fiber optic cable. The catch? You have to use the absolute minimum amount of cable possible, because every single foot of that stuff costs a ton of money. You need the most efficient layout, period. And here's our real-world example. We're looking at a map of Illinois, and we need to link up 3 cities, Belleville, Mount Vernon, and Carbondale. They all need to connect to one central communication station. Our job is to find the one single spot to build that station that uses the least amount of cable. So, where do you put it? I mean, that's the million-dollar question, isn't it? We're looking for one single point, we can call it point P, where the distance from P to Belleville, plus the distance from P to Mount Vernon, plus the distance from P to Carbondale, is as short as it can possibly be. Now, I know what you're probably thinking. Just stick it somewhere in the middle, right? But here's the thing. A triangle actually has a bunch of different centers, depending on how you measure it. And it turns out none of the usual suspects are the right answer here. This problem isn't about finding the center of mass or anything like that. It's about minimizing a total distance. We need something totally different. And this is where things get really, really cool. Our first big clue on how to solve this doesn't come from a computer or a textbook. It actually comes from nature, which, it turns out, figured out the answer to this problem billions of years ago. Just look at this. What you're seeing is a soap film stretched between 3 pens. Now, because of surface tension, a soap film will always try to minimize its surface area to conserve energy, and in doing that, it instantly creates a junction point that solves our exact cable problem. It finds the shortest possible path connecting those 3 pins. It's like a tiny, perfect physical computer. So that's the big mystery, right? How in the world does a simple soap film with no brain, no calculator, nothing, solve a pretty complex geometry problem instantly? The answer is just this beautiful, beautiful intersection of physics and mathematics. The secret sauce, the thing that makes it all work, is a very specific geometric property. That little junction point the soap film creates, it has a unique and totally consistent feature. The angles between those connecting paths are always exactly the same. This optimal spot has a name. It's called the Fermat Point. It's defined as that one unique point inside a triangle where the total distance to all 3 corners is at an absolute minimum. And what makes it so special? The defining feature is that the 3 paths branching out from it all meet at perfect 120-degree angles to each other. And this right here shows you exactly what we're talking about. You can see our 3 cities, and right there at that central hub, the Fermat Point, the 3 lines connecting everything are spread out perfectly. The angle between any 2 of those lines is exactly 120 degrees. 120 degrees. That's the magic number. If the angles at your junction point are all 120 degrees, you've done it. You have found the shortest possible total path. It's the geometric fingerprint of the solution. If you're trying to get your head around why 120 degrees is so special, think about it physically. Imagine 3 people are all pulling on a single knot, and they're all pulling with the exact same amount of force. Where does the knot end up? It settles into a point of equilibrium where it's being pulled equally in all directions. And that stable, balanced state happens only when the angles between the ropes are all 120 degrees. The soap film, our cable problem, they're all just finding that point of perfect balance. So, okay, we know the 120-degree rule works. We've seen it in nature. But why? It's not just some happy coincidence. There's an incredibly clever geometric proof that shows exactly why it has to be true. And it all involves a neat little trick with rotation. So here's the basic game plan for the proof. We start with our 3 separate cable lengths. Then, we do something that seems a little random at first. We're going to rotate one of those lengths by exactly 60 degrees. But as you're about to see, this clever move transforms our 3 separate paths into one single continuous path. And from there, it's all about making that one path a straight line. Okay, so check this out. We started with 3 separate lines, but by taking the path from Mount Vernon and just rotating it 60 degrees around Belleville, we've magically unfolded the total distance. Now, the total length of all our cables is represented by that one single connected red path you see, stretching all the way from Carbondale up to the new rotated spot from Mount Vernon. We basically turned a network problem into a straight line problem. And what's the one thing we all learn about the shortest distance between 2 points? It is always, always a straight line. That fundamental idea, something we all know, is the key that unlocks this entire proof. For that long connected red path to be as short as it can possibly be, it has to be a perfectly straight line. And because of the geometry of that 60-degree rotation we did, the only way for that path to become straight is if the angles back at our original junction point lock into place at exactly 120 degrees. A straight line over there forces the 120-degree solution back here. It's just so clever. All right, let's bring it all home. Let's connect the dots from the abstract math all the way back to our real-world problem there in Illinois. And would you look at that? On the left, we have the pure, classical geometric construction for finding the Fermat point. And on the right, that exact same geometric solution laid right on top of our map of Illinois. The math gives us the perfect, precise answer for the real-world location. It's a perfect match. And this is the final, beautiful connection. Here, we see that same geometric construction sitting right on top of the physical soap film experiment. The perfect world of mathematics and the elegant world of physics, they arrive at the exact same answer. It's incredible. So, let's just quickly recap the big ideas here. First, the shortest path connecting 3 points is found at a special spot called the Fermat Point. Second, the signature of that point is that all the paths meet at 120-degree angles. Third, amazingly, physical systems like soap films just find this point all on their own by minimizing energy. And finally, a really elegant proof shows us mathematically why that 120-degree rule has to be the answer. It really makes you wonder, doesn't it? If the laws of physics can solve a complex optimization problem using something as simple as a soap bubble, what other brilliant solutions to our own problems might already be out there in the natural world, just waiting for us to notice?